So consider a plane surface PQ immersed in a liquid of density rho. This is my plane surface PQ. So let y bar be the depth of the surface, theta the inclination of that plane, and let the change in the small dA be the change in the area of that element. So if I were to find the depth of pressure on the immersed plane surface, I will first find the force acting at this point R, the point C. So that resultant force. Now how I get that force, I'll first find the change in the small force, which is acting on that element, on the element at Q, at point Q, which will be equal to the pressure, which is rho G times Y times the area. So this pressure times area to get that force. So if I were to get the total force will be summation, be rho G summation of all those elements, the y's of all and the areas of all those elements, the depth. So now this equation here is the same as first moment of area. First moment of area. So the first moment of area. So the first moment of area is A y bar. So therefore R will be equal to rho G A y bar, and that is the resultant force acting at the point C. So the second thing I'm going to do is to find the moments acting at the point C. So if I were to have this thing again, the moment acting at the point Q, at the point C first of all, will be R. Will be R times the length, which is O times C. Now to find this equal, so to find the moment along at the point Q, that element, this will be the moment about that element will be the force, which is pressure times area times the distance, which is S. I've written. So now the moment about all the elements in that plane will be the summation of all those elements. So this is equal to R times OC. Now I want to simplify this further. So remember that Y, since these are right angled, will be equal to this S times sine theta. This S times sine theta. So if I simplify it a bit, it will be rho G S squared sine theta, and I have my area. So this is equal to, I want my rho, my density, my acceleration, and sine theta remains the same. What will change is this. So this is the second moment of inertia. So the second moment of inertia is equal to A and times K naught, where the K naught is the moment, where K is the radius of gyration about the point O. So according to parallel axis theorem, we know that this is the same as this. So what I'm then going to do is to put this back in my equation. So this will be that. So I have my R, my resultant force, as rho g times AY bar. Now remember that the derivation was to find the depth of pressure. So my depth of pressure, if I were to draw it this way, is my depth of pressure that I'm supposed to find. So R, I substitute with rho g AY bar. So OC, if I substitute, if I want to put it in terms of D, well then it will be such that D, or my OC, is equals to D over sine theta. So I come and substitute my OC with D over sine theta. I have my former equation as that. So I let these cancel each other. My A's will also cancel each other. So I now have Y bar is equals to that. So now what I want them to do is to put my H, remember I want to put my H in terms of Y bar. So if I go to the first, this is my H, I can put it in terms of Y bar. So my H is equals to Y bar over sine theta, according to trigonometry. So I come and substitute my H here with Y bar over sine theta. And I'm also going to put the Y bar over sine theta, this Y bar over sine theta to the other side, so that it becomes sine square theta over Y bar is equals to kg squared plus my Y bar squared over sine square theta. So if I remove the brackets, what I'm going to be left with is sine square theta kg squared plus Y bar. Now this is the depth of pressure. This is the equation for finding the depth of pressure. For a plane surface immersed in a fluid.